Welcome back guys, and this is the video lecture 4. And this particular video lecture deals with design of a belt drive. So in this particular video lecture I'll be covering the fundamental formulas related to design of a belt drive, and also we'll be seeing different types of a belt drive and their application, and some of the standard conditions related to those types of belt drive we'll be seeing in this particular video lecture. And so let us start with the formal definition. Let us start with the definition of a belt drive. A belt drive is a motion transferring device. Here you can see that motion transferring device. A belt drive is mainly a motion transferring device or power transmission device that are generally used to transfer the motion between the shafts by using belt and pulleys. So once again, let me repeat this. A belt drive is a motion transfer device or power transmission device that is generally used to transfer motion between shaft by using belts and pulleys. There are so many other definitions, but I feel that this was an appropriate definition. For that reason we are referring. And also I would like to tell you that a belt drive is also called as a flexible drive, whereas a gear drive is called as a positive drive. And the main advantage of belt drive over gear drive is it can transfer the motion or the power from one shaft to another shaft when they are at a larger distance. And also the initial cost of the pulley and belt are relatively very less when compared to a gear. Okay, now let us see selection of a belt drive. And see, it is this one selection of a belt drive mainly deals with why we are on what basis we can prefer a belt drive over a gear drive. That will be highlighted here. Else I can say in which situation a belt drive will be more appropriate rather than the other power transmission drives. So here, depending upon the following terms: speed of the driver and the driven shaft. Eventually we know that when we want to transfer the power from one shaft to another shaft, the shaft by which we are transferring the power, that becomes a driven shaft, and driving shaft, and the shaft which will be receiving the power will become a driven shaft. So similarly, the pulleys which are mounted over these are called as driving pulley, driver pulley, and driven pulley. Driving or driven or driver. So pulley which is making it to rotate is called as a driver pulley, and the pulley which going to rotate is called as a driven pulley. So similarly, when you want to select a belt drive as a power transmission drive, the first focus should be made over the speed of the driver and a driven shaft, and second one is how much amount of power you want to transfer. Since in a belt drive can be transferred a limited amount of power, if we want to transfer more than that, there are chances of failure in a belt, or else there will be a chances of a slip. So power to be transmitted also judge whether we can use a belt drive or not. And third one is positive drive requirement. One of the main disadvantage of a belted drive is it is inevitable of slip, which means slip will be always there in a belted drive, which causes power losses. So positive drive is the one in which almost all zero slip is there. So how much positive drive requirement is there? So depending upon that also we can able to select a belted drive. Third one, availability of a space. That is also one of the main reason. Next one is shaft layout. Whether the shafts are inline, parallel, or at an angle of 90 degrees. Depending upon that also we should know whether a belted drive is suitable or not. And the sixth one is service condition. Now when we say about the service, I would like to tell you one thing. See, even though gears are also get wear and tear, but somehow when a belted drive is used, these are more prone to some losses due to slipping and all these things, which leads to elongation of a belt, gearing and tearing of a belt, which leads to more losses. And primarily the power is transferred in a belted drive from pulley to the belt and from belt to another pulley. And when it is transferring from pulley to belt, the main source of power that is transmitted to belt is by means of a friction. Since they always have a relative motion, a wear and a tear of a mating surface will be taking place, and that causes increasing in slip. So service condition defines that at how many hours of service then afterwards you want to replace. That also that also defines whether to go with the belted drive or not. So these are the 6 parameters we'll be looking at before we will be selecting a belt drive as a power transmission device. Hope you have got it. The next one is how many types of belt drives are there. Now generally this classification what I am making is based on the type of a belt what we are using in a transmission drive. So the number 1 is a flat belted drive, number 2 is a V belted drive, and number 3 is a wire or rope drive. So the flat belted drive is the one in which here you can see the flat belted drive is the one in which the belt will be flat. If you make a section of the belt, the cross section of the belt will be a rectangular section. In order to illustrate that, here you can see the figure number 1. In figure number 1, you can see there is this one is our pulley, this one is our pulley, and this one is the belt, a flat belt. And whatever you are seeing is a half sectional front view of the belt and rope or a pulley belt and rope drive with pulley. Full half sectional front view of a belt and a rope drive with pulley. So we are seeing this. Now here you can see in case of a V belted drive, the shape of a belt is in a trapezoidal form, whereas in case of a flat belted drive, the shape of the belt is a flat. And when we go for a wire and a rope drive, you can see the wire and a rope drive will be having a circular cross section. So this is the classification of what we are making based on the type of a belted drive. Okay. Now once we have looked at the types of belted drive, now we will be having a look over different types of a flat belted drive. If you take only flat belt into account, what are the different type of a configuration, or what are the different types of a flat belted drive we can have. So starting with the number 1, that is called as an open belted drive. An open belted drive is one in which both the driver and the driven pulley will be rotating in the same direction. But here you can see that Here you can see that the driver pulley and the driven pulley, both of them are rotating in the same, that is counterclockwise, in the clockwise direction, sorry. Both the driver and the driven pulleys are rotating in a clockwise direction. And this is a schematic diagram. And if you go furthermore, if you see this figure, you can easily able to understand how the arrangement could be. Now here you can see this one. Let me color the tree. Here you can see this one is a pulley, and which is a driver pulley, and this is also our pulley, but this is a driven pulley, and both these pulleys are being mounted to a shaft. Here you can see there is a shaft. This one, sorry, clearly, this is our shaft. Okay, so what they have did, they have kept this particular driver pulley on a shaft which is connected with a motor, and here there is a driven pulley. Here you can see there is a driven pulley which is again mounted on a shaft, and these are connected by means of a belt. Here you can see that. So once it starts, when the driver pulley is being rotated by means of a shaft, it will be forcing the belt to push like this, and this belt will be making this driver pulley to rotate, and again it will be coming. So there will be a pushing action here, and there will be a pulling action here. Okay, or else I can say push and pull. So due to which one side of the belt will be subjected to a slack side, and one side of the belt will be subjected to a tight side. Slack side, tight side. Okay, and here you can also see the top view of this particular figure. In the top view, you can clearly able to see the shafts. Here this is a driver shaft and this is a driven shaft. Now this one is our width of the belt, that is represented with the B. Okay, and here this will be the thickness of our belt, that is represented with the T. Okay, so this is the general terms that are involved in a open belt drive. And also furthermore we can see some more details. Here you can see this driver pulley is making contact with the belt, and that is starting with this point A. Okay, and on the other side of the pulley or at the below, you can see it is starting the contact with the belt at this point B. Similarly, on a driven pulley, this one is actually a driven pulley. Okay, okay, so this is a driven pulley, and for a driven pulley, you can see here the belt is starting in contact with the pulley at this point. Let me say this point as C and this point as a D, and if I join these points with the center of the pulley, here you can see it is making an angle alpha, and this particular angle theta 2 is called as angle of lap or angle of contact. Okay, See, since the power is mainly transferred due to this contact or due to this contact, hence more the angle, more the power will be transferred. And now here, now for this, here for a driver pulley also you can see this total angle where the belt is in contact with the pulley is represented with theta 1. Now theta 1 can be calculated by, if I take half, that becomes 180, plus if this angle is alpha, here you can see this angle is alpha, here you can see that. If this angle is alpha, I can write 2 alpha because one is above and another one is at the below. Similarly, if theta 2 is the angle of a lap for a driven pulley, then I can write this as 180. Now here, as since alpha is here, so it becomes minus 2 alpha. So for the driven pulley it is minus, and for the driver pulley it is plus. So theta can be calculated by, I can write a common formula, 180 plus or minus 2 alpha. So this is the formula by which you can able to calculate what is an angular lap. And alpha, generally alpha will be given in the question itself, and from which we can able to calculate what is the angle of lap. So it will be given and we need to find out this. So this is what we can do. And another one is from this center of the driven pulley to the center of the driver pulley. It is called as center to center distance, and it is represented with C. C is nothing but the center to center distance. Now let us have a look on the another one type of flat belted drive, that is called as a cross belted drive. So generally a cross belted drive is preferred when the angle or the direction of rotation of the driver pulley is in one direction and the driven pulley is in another direction. At that time we'll be preferring a cross belted drive. Okay, so here you can see it is going in a clockwise direction. So driver pulley is rotating in a clockwise direction and the driven pulley is rotating in a anti-clockwise direction or counterclockwise direction. And also you can notice, in case of a cross belted drive, both theta 1 and theta 2 are same. If I say in the similar manner, this is alpha and this is also alpha. Now I can write theta. Theta will be common. Theta 1 is equals to theta 2 and that will be equals to 180 plus 2 alpha. Okay. And also you can notice here the belt is becoming there is a point at the middle of the drive where there are chances that the side walls of the belt may touch with each other, which may leads to rubbing of the belt and which may causes failure. Now you can have a very clear view here. You can see how the movement of belt is taking place. So belt will be moving from here, will be going all the way here, goes like this, and then it turns like this. Okay, it moves like this. So due to this specific movement of the belt, which causes the twisting of the belt, and due to that reason the belt are more prone to failure in case of a cross belted drive when it is relatively compared with an open belted drive. And also to avoid this rubbing, generally the width of the belt, the center to center distance C is maintained 20 times of the way. So in order to have this less rubbing action, a standard condition is being followed. That condition is C is equals to 20 times of a B. And also the velocity of the belt or the speed of the belt should be less than 15 meters per second. If we adopt these particular condition, then we can avoid or we can reduce the rubbing of the belt. Okay, once again let me repeat this. To avoid the rubbing of the belt, at the middle of the portion of the cross belt, we'll be following two conditions. One is maximum center to center distance should be 20 times of the B, and another one is velocity of the belt should be less than 15 meters per second. So from this we can also draw a conclusion is, in a cross belt drive, a limited speed can be transferred or limited speed can be maintained in order to reduce rubbing. Okay, now we'll be going for another one type of a flat belt drive, that is called as a quarter turn belt. Here you can see that. Okay, this is another one type of a belt that is called as a quarter turn belt, and it is also one of the type of a flat belt drive. Here you can see the driver pulley and the driven pulley are perpendicular to each other. Okay, and also one of the another one type here you can see the driver, if we say this as a driver pulley and this one is a driven pulley. Now these two are at an angle of 90 degrees. Here if I extend this line and if I extend this axis line of both the pulleys, these two will make an angle of 90 degrees. And here you can see there is a guided pulley. The main purpose of a guided pulley is to provide the required tension and provide the required angle what you want. Okay, so by using a guided pulley, a 90-degree turn can be also achieved in case of a flat belt drive, and this is also called as quarter turn belt drive. Now we'll be seeing another type of a belt drive in which we'll be using an ideal pulley, that is called as IDLR. So here you can see, let us say this is a driver pulley and this one is a driven pulley. Now if at all the size of the driven pulley is very small when compared to a driver pulley, the required angle of a contact could not be achieved. Or else, let me tell you in this way: if the size of both the pulley is compared, if one of the pulley is very small when compared to another pulley, then the required angle of a contact between the belts and the pulley may not be there. So in order to transfer the power in such type of belted drive, what we'll be doing, we'll be using a IDLR pulley so that the required power can be transferred. And here is another one example where we can also able to use the IDLR pulley. Here you can see there is a one driver pulley and 1, 2, 3 are the driven pulleys, and also these are provided with 1, 2, 3, 4 IDLR pulley. So when the power is to transfer from one driver to multiple driven pulleys, we will be using this type of arrangement, and that type of arrangement is called like a belted drive with IDLR pulleys. The next one is a compound belted drive. In a compound belt drive, you can see that here you can see that 1, 2 and 3, pulley number 2 and pulley number 3 are mounted on a same shaft. Okay. Mainly this type of pulleys are used when a larger speed increase or larger speed reduction ratio want to achieve, then we'll be using this type of arrangement. Suppose here you can see, if let us say the pulley number 1 rotate for 1 time, which leads to pulley number 2 to rotate for 2 times. Now this pulley will also rotate for 2 times since they are being mounted on the same shaft. Now when it goes to here, then it becomes 4 times if they are maintaining the same speed ratios. So if you want to achieve a increasing a higher amount of speed ratios, then you will be using this compound belt drive. The name itself indicates that it compounded. It compounds. Okay. Next one of the example is a step con pulley. In case of a step con pulley, we can able to achieve a multiple speed ratios or velocity ratios. Here you can see, by changing this belt, this is belt which is kept in one position. Now by changing the belt on different steps of a step pulley, we can able to achieve our required amount of speed ratio. Okay. Now this type of arrangement mainly you can see in case of a lathe headstock. In case of a lathe headstock, we'll be finding a same arrangement. So these are the few types of flat belted drives. Once again, let me repeat that: open belted drive, cross belted drive, water turn belted drive with idealer pulley, compound belted drive, and step con belted drive. But another one thing, let me tell you here, as per design and problems are concerned, as per JNTU syllabus, we'll be dealing with open belted drive and a cross belted drive in case of a flatted belted drives. And furthermore, the other type is not there, so we'll be only covering the first two. So let us know what are the various formulas that are involved in first two. And these formulas are very important when you are doing calculations. So first one is the belt velocity. So linear belt velocity can be calculated by formula pi d n 1 by 60 and pi small d n 2 by 60, where d is the diameter of the dia of driver pulley. Okay, small d is dia of driven pulley. And these should be equal. And when these should be equal, since the velocity of the belt on both the pulleys should be same, so these should be equal, and that can be calculated by using this particular formula. And if they are equal, if we equate that, then we can get a relation that is called as the velocity ratio or speed ratio, that is d1 by d2 is equals to n2 by n1. Okay, and this particular formula, in which we haven't considered the thickness of the belt and slip, we haven't considered slip, and also we haven't considered creep of the belt. So if we consider that, so same velocity ratios that are this, if we consider thickness, that formula will be changes to this one. So we will be adding TT here, where T is nothing but the thickness of the belt. Next one is along with the slip. When we consider the slip, the velocity ratio formula will be changes to this one. Here you can see that where S is nothing but total slip. Now what is the slip actually? Let me explain you. The slip is a phenomena in which the movement of pulley without the movement of a belt will be taking place. A slipping of a pulley and belt will be taking place, due to which there will be a loss in power, and that is called as a slip. Now here you can see percentage of slip S1, slip between the belt and the pulley, driven pulley. S2 is nothing but slip between the belt and driver pulley. S2 is the slip between the belt and a driven pulley here. And if we add this, we will be getting total slip S. S is equals to S1 plus S2. So this particular velocity ratio formula is along with slip, and which means we are considering slip also. If there is no slip, then d by capital D by small d is equals to N2 by N1 only. Now similarly, if I consider velocity ratio along with creep. Now what is a creep here? Creep is nothing but stresses that are induced due to sustained load. Now since the pulley will be, the belt will be wrapping the pulley continuously when it is under service, and there will be a tension at one side and slack at the other side. There will be a tension on either sides, and due to this sustained forces or sustained tension forces, there will be stresses induced in the belt. And you can also notice that when we watch the operation of a flat belted or a larger size of a flat belt drive with our visual inspection, when we see when the belt is moving over the pulley, you can able to notice that the belt which is there on the pulley will be getting curved out. You can notice that when you see any flat belt drive under operation. Now if we consider that, so overall that tells you that the belt under operation will be subjected to stresses, and those stresses are due to creep. Okay, now here if we consider creep into account, then E into under root of sigma 2. Now sigma 2 indicates stresses due to creep on a driven pulley. And sigma 1 is, you might be guessing this, it is stresses in driven pulley. Driver pulley. These are the stresses. Okay, so suppose in a problem he is mentioned consider the creep in the power drive or the belted drive, then you need to consider this formula. Now overall this formula will be changes to this one, that is capital D by small d is equals to N2 by N1 into, I can write, if I consider slip, it becomes S by 100. Okay, if I consider the thickness of the belt, this will be changes to T here. And also if I consider the creep into account, then this formula will be changes to this. So this is the overall formula of velocity ratio. When you consider thickness of the belt, also you are considering slip in belt and pulleys, and also you are considering creep are the stresses that are induced due to creep forces or creep due to creep, I can say. Okay, now next particular formula is the length of a belted drive. So length of the belted drive. Okay. Now since if you take a flat belted drive, the center to center distance between the shafts are different in different application. Now generally the flat belts are made in a very long in a bundle, and after making all the necessary assembly of a shaft and pulleys, then what you will be doing, you will be keeping a belt over that. First you will be cutting your required length, then you will be keeping on that, and the two ends of the belt, in order to make the belt into a loop. So let us say first we have a driver pulley here and a driven pulley here. So first what we will be doing, we will be calculating the length of the belt, and then we will be keeping the belt on these two pulleys. Then by using some type of fixing method or joining method of this belt, like bolting, clamping, those type of things we'll be doing, then we'll be keeping that. So when we go for a design of a belted drive, we should also calculate what should be the length of the belt so that we can buy that. So the length of the belted drive is nothing but when you cut this belt and you keep that in a straight manner, that becomes the length of the belt here. Okay, so that particular length can be calculated by using this particular formula if at all it is an open belted drive. 2C indicates center to center distance, capital D indicates diameter of the driver pulley, and small d indicates diameter of the driven pulley, and so on. So if by this I can able to calculate the length, then I can able to keep on my setup, initial setup what we have made, and then two ends of the belt can be joined by using a operation. I can quote one of the best example here. If you see a wheat floor machine, you can find that the belt will be, ends of the belt will be bolted together. Okay, so that type of arrangement will be made. So for that reason we need to also calculate the length. Similarly, I can able to calculate length of a cross belted drive by using this particular formula. There will be a small change. Here it is negative and here it is positive. That is only the change. And next one is tension ratios. See, again another one thing I would like to tell you, here we are not going for the derivation part. Since we are dealing with the design of a belted drive, there is no need to go in detail about the derivation part. Even though if you want to know how these equations are, these particular formulas we are getting, you can refer either Kurmi or Bhandari textbook. In that it has been given clearly. Only just here I am giving briefing over the formulas what will be coming across in the design of a belted drive. Now here you can see when we consider tension ratios are indicated T1 by T2 is equals to e to the power of mu theta, where mu is coefficient of friction and theta is angle of lap or contact between the belt and the pulley. Okay, so T1 by T2 equals to e to the power of mu theta. What is T1 and the T2? Tension on the tight side, tension on the slack side. So in order to explain that, here you can see that we can refer a force diagram of a belt and a pulley. So this one is a slack side and this one is our tight side. So if I draw the force diagram or free body diagram, you can see, so the tensions will be acting in this way. Tension on the tight side is represented with the T1 and tension on the slack side is represented as T2. So that ratios of this tension will be equals to e to the power of mu theta. E to the power of mu theta. And there is another one simplified formula in which you don't find an exponential here. E, that is 2.3 log of T1 by T2 is equals to mu into theta. You can also use this particular formula, and be careful while using this formula. Theta should be here in terms of radians. Okay, theta should be in terms of radians in this particular formula. And this particular formula, that is T1 by T2 is equals to e to the power of mu theta, will be changes to another one formula when you are considering centrifugal tension into account. Now what is centrifugal tension? Let me explain you. Let us say there is a pulley here. Let us say there is a pulley like this. Okay, and over that pulley the belt is been wrapped or overlapping like this. If you take a small mass of the belt, let us say this is belt, okay, this one is our belt. Now if we consider a small mass of the belt, since the pulley is always rotated, the belt will be subjected to a centrifugal force, and that particular centrifugal force is represented as Pc, and that can be calculated by mv square, where m is mass of the belt and v is a velocity of the belt. Okay, so centrifugal tension, and here capital T1 is the total tension on the tight side. Total tension on the tight side, that is T1 plus Tc. Okay, then capital T2 is capital T of T2 is tension on a slack side along with centrifugal tension. Now if I consider the centrifugal tension into account, and generally since centrifugal tension is related with the mass of the belt, for a smaller size of the flat belt drive or any belt drive, the mass will be very small. Since that's the reason centrifugal tension is negligible. But somehow if you take into account a very larger belt drive, there the size of the belt will be also large or big, I can say. So centrifugal effect will be also there. So in order to consider that also, we can use this particular formula, and from this I can able to write what is T1. T1 is equals to capital T of a T minus a Tc. So similarly I can write a T2 is equals to capital T1 minus Tc. How Tc can be calculated? Using formula mv square. Okay, this is the standard formula to calculate forces due to centrifugal effect. So this particular formula will be changes to this particular formula when you are considering centrifugal tension into account. So next there are some more basic fundamental formulas here, like already we have discussed angle of lap can be calculated by using this particular formula, and in that alpha can be calculated by using this if at all it is an open belt drive, and if at all it is a cross belt drive, then alpha can be calculated by using this particular formula. Similarly, power transmission in case of a belted drive can be calculated by using this particular formula. Okay, so how we have got this formula? Now you can, if we go back to the free body diagram of a belted drive, since on a pulley, the tension forces that are acting are T1 and T2. So net effective force that is acting on the pulley can be written as T1 minus T2. Okay, now once we know force, then if we multiply it with the velocity, you will be getting power. So T1 minus T2 into V, from which I can able to get the power. And this will be in terms of watts. If you want in terms of kilowatt, this can be divided with the 1000. And here are some of the very important conditions for maximum power can be transferred by achieving these two particular conditions. The conditions are: the centrifugal tension should be T1, capital T of a T1, it is the total tension on the tight side along with the centrifugal tension divided by 3. If this will be equals to the centrifugal tension, then the maximum power will be delivered by the belted frame. Similarly, or else we can have another one condition: velocity of the belt should be equal to under root of capital T1 by 3m. If we attain these two, any one of these two conditions, then a maximum power can be transferred by means of a flat belted drive. Hope you have got it. Also, I would like to add another one small statement here, that these formulas are already there in the design data book. Only the main purpose of this particular video lecture is to tell you what are the significance and what are the values that are there in these particular formulas. For that reason we are discussing this, and please go through this formula. And also I suggest you to make a note of all these formulas what we are discussing in this video lecture 4, so that it will be very helpful for you while solving a problem. Thank you.